Welcome to the video lecture on hyperbolic functions. Hyperbolic functions arose from a comparison of the area of a semicircular region with the area of a region under a hyperbola. So here is half of a unit circle from -1 to 1 centered at the origin, and if we wanted to compute the area underneath that curve has as its equation y equals square root of 1 minus x squared. So if we integrate that from -1 to 1, the integral turns out to be 1/2 parentheses x square root of 1 minus x squared plus the arc sine of x. And when you plug in -1 to 1, you end up getting the area of half of a circle with radius 1, which is pi over 2, or about 1.571. Now, if instead you integrate or find the area underneath the curve y equals the square root of 1 plus x squared, that equation is the equation of a hyperbola. So if we integrate the plus case from -1 to 1, look at how they differ. You get 1/2 x times the square root of 1 plus x squared, and instead of getting an arc sine of x, you get what's called hyperbolic sine, or sometimes we just call this sinh of x. And when you plug in -1 to 1, this is approximately 2.296. Okay, so that's kind of where it comes about from. What you're going to need to know are the basic definitions of these hyperbolic functions. So the hyperbolic sine, or sinh of x, is defined to be e to the x minus e to the negative x over 2. Hyperbolic cosine, or cosh of x, is e to the x plus e to the negative x over 2. So same as sine, but with a plus sign in between. Hyperbolic tangent is hyperbolic sine over hyperbolic cosine, and then hyperbolic cosecant, secant, and cotangent are just the reciprocals of their corresponding functions, just like we would normally do for the regular trig functions. So these are the major two definitions that are going to be new for you. Notice that these hyperbolic functions are defined in terms of exponentials. Okay? So let's develop a few identities and prove them. So we know that for the unit circle and the Pythagorean identities for our normal trigonometric functions, we know that cosine squared x plus sine squared x equals to 1. Well, it turns out that hyperbolic cosine squared x minus hyperbolic sine squared x is equal to 1. And let's prove that just using those definitions we just talked about. So hyperbolic cosine, remember, was defined to be e to the x plus e to the negative x all over 2, and we want to square that. And then we want to subtract from that the hyperbolic sine quantity squared, which is e to the x minus e to the negative x all over 2 quantity squared. And we're hoping that this is going to equal 1. So if we square this out, I'm going to have to FOIL the top here. This is going to give me an e to the x times an e to the x, which is an e to the 2x. Then I'm going to get an e to the x times an e to the negative x. Now think about that. So basically what we're doing here is we're FOILing. Let me write it out so you can see. So e to the x times e to the x was e to the 2x. Then I'm going to get an e to the x times an e to the negative x. Since the bases are the same, you add the powers. X minus x is 0, so e to the 0 is actually going to be a 1. And we're going to get another one of those from this other middle term. So we're going to get a plus 2 in the middle. And then we're going to get an e to the negative x times an e to the negative 2x, or an e to the negative x times an e to the negative x, which is an e to the negative 2x. So that would be the term on the end. And the 2 squared on the bottom becomes a 4. So that's all of this squared out. Now, this one is going to be exactly the same, but the middle term will be minus because this sign in between is a minus. So we're going to still get an e to the 2x, but we'll get a minus 2, and we'll still have a plus e to the negative 2x. Now we want to distribute this negative across, and I'm going to go ahead and consolidate this into a single fraction with a denominator of 4. So we'll have e to the 2x plus 2 plus e to the negative x, and then we'll have a minus e to the 2x a plus 2, and a minus e to the negative 2x. So this cancels. I forgot my 2 there. This cancels, and 2 plus 2 is 4, and 4 over 4 is 1. So that's our proof that this is our identity, Pythagorean identity, if you will, for the hyperbolic cosine and sine. So instead of adding the squares to get 1, you subtract to get 1. Now also remember an identity from our trigonometric functions, the double angle identity. Remember that we know that sine of 2x is 2 sine x cosine x. Well, it turns out that that same idea is true for the hyperbolics. So 2 sinh x cosh x equals sinh of 2x. Okay, so let's prove this. So what we're going to do, I'm going to start with this left-hand side, and I'm going to write 2 times hyperbolic sine of x, which is the e to the x minus e to the negative x all over 2. That's how it is defined. And hyperbolic cosine is e to the x plus e to the negative x all over 2. So one of these 2's is going to cancel, but we'll still have 1 left in the bottom. And now let's FOIL across the top. E to the x times e to the x is e to the 2x. We'll get a minus e to the negative x times e to the x and a plus e to the x times e to the negative x. So those 2 middle terms actually cancel out. This is a difference of 2 squares. Then we'll get a minus times a plus e to the negative x times e to the negative x, which is e to the negative 2x. And this is exactly what hyperbolic sine evaluated at 2x would be. Remember that hyperbolic sine is defined to be e to the x minus e to the negative x over 2. So if I change this x to a 2x right here, then this changes to a 2x and this changes to a 2x. So that's exactly what we have right here. So this is sinh of 2x. So that's our proof that it worked. Okay, so some of your identities for the hyperbolic functions will be the same as for the regular trigonometric functions, but not always. Like this one was a little bit different. Okay, let's look at some of our derivative and integral rules. Derivative of hyperbolic sine of u is hyperbolic cosine of u times u prime. So that's just the same as derivative of sine is cosine. In regular trig functions, we know that the derivative of cosine is minus sine, but in this case for hyperbolics, that minus doesn't need to be there because the derivative of hyperbolic cosine is just hyperbolic sine. Okay? And we know that the derivative of tangent is secant squared, while the derivative of hyperbolic tangent is also hyperbolic secant squared. So that one's the same, this one's the same. The cosine one is different because there's no negative that's needed. So those are the derivative rules. So now let's go in reverse. If the derivative of sinh is cosh, then the integral of cosh is sinh. So this will be the integral of hyperbolic cosine is hyperbolic sine plus c. If the derivative of cosh is sinh, then the integral of sinh is cosh. So this will be cosh of u plus c. And if the derivative of tang is hyperbolic secant squared, then the integral of hyperbolic secant squared is going to be tang. Okay? So those are some derivative and integral rules. Those are going to be the only ones you're responsible for knowing. So let's practice using them a little bit. What's the derivative of x? Hyperbolic sine of x minus hyperbolic cosine of x. So to take this derivative, remember that this is an x times hyperbolic sine of x. So you must use a product rule right here. So we're going to do the first times the derivative of the second. Derivative of sinh is cosh. So this is going to be cosh of x. So that's first times derivative of the second plus the second times derivative of the first. Derivative of x is just 1. Minus derivative of cosh is sinh. So this is just going to be sinh x. We don't need an extra negative in there. That minus just comes from the subtraction. And this is a plus sinh and a minus sinh, so these actually end up canceling out. So this is x cosh x. Okay? How about the derivative of the ln of hyperbolic cosine of x? Well, remember, the derivative of ln of stuff is stuff prime over stuff. So whatever you see here goes in the bottom, and the derivative of that goes in the top, and the derivative of cosh is sinh. And what is sinh over cosh? Well, that's tangent. That's hyperbolic tangent. So if you want, you could rewrite that as hyperbolic tangent of x. Okay? All right, let's try a couple of integrals. What's the integral of cosh squared x minus 1 times sinh of x minus 1 dx? So in order to do this, we're probably going to need to do a little bit of a u substitution. There is an obvious sort of inside function, this thing in the parentheses. So if we let u be x minus 1, then du is the derivative of x minus 1, which would just be 1 times dx. So du just becomes dx. So this rewritten becomes cosh squared of u, sinh of u, and this dx becomes du. So at least we got rid of the stuff in parentheses. Now, when I see an integral like this with that cosh squared, what I normally do is I pull that square out and put it outside of parentheses, because then it becomes a little more obvious what to do next. When I see something like this, there's an obvious outer square right here. I'm going to call that f. This is my inner function g, and the derivative of cosh is sinh, which is exactly what I have right here, so there's my g prime, which means this is pattern recognition. So all I have to do is integrate that outer power. The integral of a square becomes a cube over 3. What's inside stays the same. And then if I just turn this back in terms of x, I'm going to replace that u with my x minus 1. So my final answer will be cosh of x minus 1 quantity cubed over 3 plus c. Okay? All right, how about this one? The integral of cosh of square root of x over square root of x dx. So same idea as the last one. Immediately I see that there's kind of this inner function right here. So let's let u be that square root of x. So that means that when you see a u being a whole square root, remember our trick is to normally square both sides first before you take the derivative, and that means 2u du is going to become our dx. So let's start substituting in. In the numerator, we have cosh of square root of x, and that square root of x becomes our u. The square root of x in the bottom also becomes our u, and the dx becomes our 2u du. So this u and this u can cancel each other out, and this 2 can be pulled all the way out front. So this whole integral just became the integral of cosh u, which is just sinh u. So this becomes hyperbolic sine with that 2 in front, and if we substitute back in terms of x, this is 2 hyperbolic sine of the square root of x plus c. And that's it. Okay, and then the last one here. Suppose that we have power cables suspended between two towers, forming the catenary shown below. So the catenary is the way that this wire sort of hangs, and this is a very common application of these hyperbolic functions, because this is a hyperbolic cosine curve right here. The shape of that hanging wire forms a hyperbolic cosine. So the equation of this catenary is y equals a cosh x over a. The distance between the two towers is 2b. So the way I set this up is I centered it at the origin. So one tower is b to the right and one tower is b to the left. What we want to know is we want to find the slope of the catenary at the point where the cable meets the right-hand tower. So we want to know this slope right here. Okay? Well, what is slope? Slope is a derivative. So basically, we need to know the derivative at that point. That's what this is asking for. So we want the derivative at this point, which is when x is what? Well, at the top of that tower, x is b. So we want the derivative at x equal to positive b. So here's my function. This is the equation of that catenary. So if we want the derivative, that's y prime, we need to take the derivative of this function. Now the a out front, a is a constant, okay? A is a constant in this problem. Only the x is the variable. So a is a constant multiplier, so it's going to stay there. And then to take the derivative of cosh of x over a, this is really cosh of stuff. So we need to use a chain rule on this. We're going to take the derivative of that outer function first, the cosh, and the derivative of a cosh is a sinh. So this is going to be sinh of the same stuff that I had before times the derivative of this inner function. And x over a is like 1 over a times x. So the derivative of x over a is the derivative of 1 over a times x, which is just that coefficient in front, that 1 over a. So my chain rule was derivative of the cosh, which is why this turned into a sinh, times the derivative of the x over a, which is this constant right here. If I simplify, these cancel, so the derivative function is hyperbolic sine of x over a. So now we can use this point, so if we plug in x equals to b, then the slope will be hyperbolic sine of, I'm going to substitute in b for that x, so it's going to be hyperbolic sine of b over a. So that's this slope right here. Okay, so I'm just giving you some very, very basic knowledge of hyperbolic functions. One very common example in the real world are these catenaries that you hear about every once in a while. And I'm just letting you know about some of the basic derivative and integral rules and the basic definition of what's hyperbolic sine and cosine are defined to be. Remember those e to the x's plus or minus e to the negative x over 2. So you just need a very basic knowledge of these functions. All right, that concludes our lecture on hyperbolic functions. Good luck.